Swayam Prabha. Digital India. Educated India.
The discussion point of today's will be on Lagrange equations, Lagrange equation and conservation principles. Conservation principles. Okay, so this is going to be part 1 of our long lecture series. The part 2 will focus on some nice problems involving these topics. And the key concepts we are going to cover, the key concepts that we will be covering are those on generalized coordinates, configuration space, Lagrange equations, and Lagrangian and the symmetry of Lagrangian. Okay, so we will start with the type of constraints in the system. We could have typically, the type of systems to begin with. We could have either a constrained system, or we could have an unconstrained system, depending on the type of problems we are considering. Now, a constrained system, typical example could be the swinging pendulum, because the pendulum is attached with the wall via a fixed rod. So the constraint is the distance of the bob of the pendulum. So this example involves the distance of the bob from the wall is going to be fixed. So this distance is fixed, let's say A. So A, which is fixed. So then this is this motion is an example of a constraint system. We could have fixed length. So we could have constraints like fixed length, or we could have constraints like fixed tension in the string, and so on. So these are typically various external constraints on the system, and depending on the various external connections. Now, unconstrained systems are those where particles are moving independent of each other. So particles move independent of each other. Particles are moving independent of each other, and in this case, the motion is governed by Newton's second law. So this is as simple. So in unconstrained system, writing equations of motion is very simple. We could clearly use Newton's second law, MI VI dot being the acceleration, rate of change of velocity is Fi being the external force. So so that is a very broad classification of the type of problem. And now we could, well, for example, let us try to write some equations of motion for one of these systems. Let's say an unconstrained system. Constrained system, I've already mentioned, for example, the motion of a pendulum, and we had seen these examples in the past. So unconstrained system, for example, the example that I have is we would like to write the Newton's law, the Newton's equation for a two-body. So this is just an example, a two-body gravitation problem. Right? So the solution is isolated system. The solution is an isolated. So this example of two-body gravitation problem is an isolated system, and it is solely mutually moving under the action of gravity. Right? Moving under mutual attraction, moving under mutual attraction. Okay, so we have mi vi dot is equal to m1 m2 g r2 minus r1 divided by, so I'm writing now, I'm writing the Newton second law for both the system of particles. So let us call this m1 v1 dot. So this is r2 minus r1 divided by r2 minus r1 cube. So this is my law of gravitation. And then what we have is, similarly I can write for the second particle m2 v2 dot is, this is m1 m2 g. This time it will be r1 minus r2 and divided by mod of r1 minus r2 cube, right? So this one, well, both of the right. So that this problem is as simple as that, writing the equations of motion for unconstrained system. So the problem now is, let us now come back to our discussion on the constrained system. Let us talk about what type of constraints we could have. The first type we could talk about are those involving only fixed length or constraints which are typically integrable. So we are talking about constraints, and let us say that we are the first type of constraints that we can involve is those of geometric constraints. Geometric constraints, and these involve only position. These involve only position vector r(i), right? Or we could also have kinematic constraints. Kinematic constraints, and these involve both position vectors ri and the velocity vectors vi, right? So typical examples could be a bob of pendulum of fixed length from a fixed point of support. So bob of pendulum remains, so this remains fixed from the point of support, okay? So this is a case of geometric constraints. Another case could be, an example could be where a particle on a rigid body which remains on a fixed distance from each other. So suppose you have a rigid body and you are considering two particles, let's say P1 and P2, and whatever happens to the motion of this rigid body, the distance between the two particles is always going to be fixed because it's a rigid body. So that is also a case of geometric constraint. So particle on a rigid body, particles on a rigid body must remain at a fixed distance from each other, right? And then we could have particles sliding on a wire. This is another example, particles sliding on a wire must not leave the wire. So the fact that the distance between the wire and the particle is 0 must not leave the wire. The fact that the distance is 0 between the wire and the particle, so these are all cases of geometric constraints because it involves some sort of position vectors in the system. And then we could also have another case where we have a contact particle of a rolling body. So contact particle of a rolling body on a fixed surface, So we are talking, let's say, a circle, and the circle is moving on a fixed surface, and we are talking about a contact particle on the circle. So there will be a constraint. So for such a case of a contact particle, let's say Q, there will be a constraints on the motion of this contact particle Q, which will involve the velocity at this point Q. So this is a case which involves the velocity VQ, velocity of the contact particle. Hence, this is a case of kinematic constraints. Kinematic constraints. Okay, so then let us take more examples. So we have let us now first discuss what are the problems involving systems having constraints. So problems in constraint system. So there are two major problems involving constraint system. The first one is that typically the Newton's equation will not apply. That is the major problem, because the Newton's equation themselves do not include constraints as such. And the second problem that we encounter in writing down the Newton's equations of motion is that the constraint forces are typically unknown. And that's why we typically cannot use classical mechanics or Newtonian mechanics, whilst writing down the model for constraint system, right? So let me write down the two problems. So the Newton's equation do not include constraints, and they must be included using additional constraints. They must be included using additional constraints. Okay, so then the second problem that we have is that the constraint forces are unknown. The constraint forces are unknown. So these are the two problems, and typically to avoid these two problems, we could typically use the method of generalized coordinates. Right? So and then the moment we are using generalized coordinates, we are talking about the Lagrange equations of motion. The Lagrange's equation of motion. Okay, so then generalized coordinates. So what are generalized coordinates? So we can assume that first of all, we can assume that the system only depends on geometric constraints. Why? Because solving constraint motion using geometric constraints is far easier than those involving kinematic constraints. So we are assuming the system has only geometric constraints. System subject to geometric constraints only. Geometric constraints only. Right? So we can talk about a set of position vectors. Which are consistent with the geometric constraints. The geometric constraints is called a configuration, right? So a set of position vector consistent with the geometric constraints is called a configuration. And typically now we are ready to write down the definition of generalized coordinates. We see that if the configuration of a system is determined purely by the set of some independent variables, then those independent variables are said to be the generalized coordinates of the system. So let me write down what I just said. So if the configuration of a system S is determined by the values the values of a set of independent variables, Qi's, then Qi's are said to be the generalized coordinates of the system, right? So that's what we have. Okay, so then automatically it comes to the point that generalized coordinates are independent variables. They are independent variables. Because why? Because if or it is equivalent to saying that there does not exist any functional relationship in between any of the coordinates. So there does not exist a functional relation between any generalized coordinates. Otherwise we could remove the extra coordinate by using that functional relation. Remove that extra coordinate and by using the relation, by using the functional relation. Okay, so then the other case could be that the generalized coordinates q1, q2, qn, they determine the configuration of the system. They determine the configuration of the system S, right? That is for all position vectors Ri. We could have that Ri can be written as Ri of q1, q2, qn, right? So I is from 1 to n. Okay, so then let us look at an example. So the example that we have is, we would like to find the generalized coordinates of the following system. So let the system S consists of two particles P1 and P2 connected by a light rigid rod of length A, right? So P1 is constrained. Let's say P1 is constrained to move along a fixed horizontal rail, and the system moves in the vertical plane. Vertical plane through the rail. Okay, so we need to find the generalized coordinates. So select the generalized coordinates and obtain expressions for R1 and R2 in terms of these coordinates. Okay, so what are we talking about? We have a system of two particles. One is allowed to move on a fixed rail. So this particle 1 P1, and this is allowed to move along the horizontal direction, let's say X. And then we have a second particle which is hanging with from the first particle at a fixed distance, let's say A. And the second particle P2 is allowed to, of course, rotate. So this is the rotation angle theta. Okay, so this is what the problem says. We need to find the generalized coordinates, and of course we can see that due to constraints on particle 1 and particle 2, we have that the generalized coordinates automatically come out to be x and theta, where x is the horizontal distance moved and theta is the angle that the second particle makes with respect to the vertical. So these are my generalized coordinates, and if I were to write the position vectors, then for r1 this is x of I, and for r2 this is going to be x plus a times sine theta of I minus a cos theta of k, where my direction, I must set up my frame of reference. My I direction is the horizontal direction and k is the vertically upward direction. Okay, so hence we have a minus sign, minus a cos theta k, right? So this is coming from pure geometry here. So that is a very simple problem, determining the position of the system using the generalized coordinates. The generalized coordinates are the independent variables here, which are x and theta. A is a fixed number, so that is not a variable. Okay, so then let us look at another example that I have. So the third example that we have is we need to choose the generalized coordinates for a system of three particles, P1, P2, P3, where P1 and P2 are connected by a light rigid rod of length A, and P2, P3 are connected by a light rigid rod of length B on a horizontal table. Okay, so what we have is we have a set of three particles P1, P2, P3, so P1 and P2, right? And these are all connected by a system of light rigid rods of length A and length B. So P1, P2 is connected by a light rigid rod of length A, and P2, P3 is connected by a light rigid rod of length B. And what we have is we have to find out the generalized coordinates. Now, the point is that these points are all the distance between these three point particles are fixed. So the only thing or the only movement can come around by the various angles of rotation of these connections. So we could have a combination of two angles serving as the generalized coordinates. So one could be we could have the angle that the rod P1, P2 makes with the horizontal, or equivalently this is the same angle theta. So this is the same angle theta that is P1 is making with the horizontal, and we could have the second angle which is P2, P3 which makes with the horizontal, so phi, right? So we have this one and we have this one, or we could equivalently define another set of generalized coordinates where we could have another coordinate here theta and another coordinate here phi, and that is what we have, right? So these are the three coordinates. And also we are also given, well, what else are we given? I think we are also not given what are the coordinates. So we have to also take one of the coordinates of the particle. So let's say P2 has a coordinate x comma y. So moment we fix one of the coordinates of the particle, then the rest of the other two particles are already connected to each other with a light rigid rod. So those lengths are fixed. So in total we have about four four generalized coordinates. One is, two of them are the xy coordinates of one of the particles, let's say p2, and we could have another set of generalized coordinates. I'm just discussing two sets of generalized coordinates. We could have multiple, depending on our choice. So the second, if we look at this particular diagram, the second is the angle theta that P1 makes with the horizontal, and the third is the angle phi that P2 makes with the horizontal. P1 P2 makes with the horizontal, and the second one is P2 P3 makes with the horizontal. So we have a total of four coordinates here, and that's it. Okay, so now let us talk about another concept known as the so-called degrees of freedom. So what are degrees of freedom, DOF? So degrees of freedom in a system are the number of generalized coordinates. So let me write down the formal definition. So let S be a mechanical system subject to geometric constraints, then the number of generalized coordinates needed to specify S is called the degrees of freedom. Degrees of freedom of S. Okay. So the point is, this particular definition gives a clear-cut relation between the degrees of freedom and the generalized coordinates, and eventually the number of equations of motion of the system. It turns out that the number of generalized coordinates is equal to the degrees of freedom of the system, and that is also equivalent to the number of equations of motion describing the system, because the degrees of freedom or the number of free variables are going to dictate how many equations we need to solve the system completely. Okay, so what I just said is that the degrees of freedom and equations of motion, they are that the number of degrees of freedom of a system is equal to the number of equations of motion. Okay, so that is what we have, so that is the primary relation. So I think at this point I'm all out of time for the first module, and in the next module I'll be talking about, to begin with, I will provide some quick examples describing what are degrees of freedom, and then later on we will look at some interesting examples solving the constraint system using Newtonian mechanics, and then eventually we come to the point where we derive the Lagrange equation of motion, which will be the basis of our discussion so far. So thank you so far for listening.